What is the smallest thing that exists, and what is the largest? If you guessed atoms and galaxies, you're not off by a little. You're off by an entire universe of scale human senses were never built to notice. Below the smallest atom sits a wall reality itself cannot cross. Above the largest galaxy sits a structure so vast it seems to break the rules that limit how big anything can get. And right now, the farthest reach of our species, every signal humanity has ever broadcast into space, has barely crossed 100 light-years from where you're sitting. Chapter 1: The Quantum World. Zoom in, past the skin of our bodies, past the cells, down to the molecules that build them, and you reach the atom. The thing most of us were taught in school is the basic unit of matter. Picture an atom the size of a football stadium. At the very center, there's a marble. That marble is the nucleus, and it holds almost all the mass of the entire atom. Everything else, the seats, the field, the open air above them, is empty space, patrolled only by electrons moving too fast and too strangely to ever be pinned to one spot. They don't orbit like tiny planets. They exist as a kind of blur, a probability, a shell of maybe here, maybe there, that happens to be dense enough to stop your hand from passing through a wall. That's the part most people never get told. When you touch something solid, you are not actually touching it. You are feeling the electrons in your fingertips refuse to get any closer to the electrons in the object. Every handshake, every footstep, every moment your body doesn't fall through the ground is really just static repulsion holding empty space against empty space. If you removed all that emptiness from every atom in a human body and pressed only the solid parts together, the entire person, bones, organs, blood, everything, would compress down to something you could hold in the palm of your hand. Same mass, fraction of the size. That's how much of you is actually just room. To put a number on that emptiness, if the nucleus of a single atom were scaled up to the size of a marble sitting on the pitcher's mound of a baseball stadium, the nearest electron would still be circling somewhere out past the parking lot. Everything in between, all of it, is open space. This isn't a rare property of a few unusual elements. It's true of the chair under you, the phone in your hand, the walls of the room. Nearly everything you have ever touched is built almost entirely out of nothing, held together by forces too small to see and too fast to feel. So what is that marble in the middle made of? For a long time, physicists thought protons and neutrons were the final answer, the smallest pieces there were. Then they smashed those particles together at enormous speeds and found something stranger underneath. Quarks, locked together in groups of 3, held by a force so strong it has its own name, the gluon, because its only job is to glue. Outside the nucleus, the electrons belong to a completely different family, called leptons, and they appear to have no size or structure at all, just points of pure charge, moving. And connecting all of it are the bosons, the message carriers of the universe, the particles that let one piece of matter know the other piece exists at all. The most familiar boson is light itself. None of this was guessed at from an armchair. Finding it required building machines large enough to accelerate particles to nearly the speed of light and slam them together, just to catch a glimpse of what falls out of the wreckage for a fraction of a second. It's a strange kind of detective work. You never actually see a quark sitting still. You only ever see the debris of a collision violent enough to briefly expose what was hiding inside, something you'd otherwise call solid. Here's the part worth sitting with for a moment. An electron sitting in your body right now is identical, not similar, identical, to an electron on the far side of the observable universe. The universe didn't design a different set of parts for every place. It built the whole thing, from your fingernail to the farthest galaxy, out of the same tiny handful of pieces, repeated over and over at every scale. But there was still one question nobody could answer. Why do some of these particles weigh anything at all, while others, like light, have no mass and can never slow down? The answer came from a British physicist named Peter Higgs, who proposed something almost embarrassingly strange in the 1960s. The universe isn't empty, it's filled with an invisible field, now named after him, that every particle has to move through. Some particles slip through it without resistance and stay massless, racing along at the speed of light forever. Others drag against it, and that drag is what we call mass. You are heavy, not because matter is naturally heavy, but because your particles are constantly wading through something you cannot see, hear, or touch. Think of it less like a wall and more like wading through waist-deep water, while someone standing beside you walks through empty air. You both start moving at the same time, but the water slows you down, gives you weight, gives you resistance, and the person in the air never feels a thing. Multiply that difference across every particle in your body, trillions upon trillions of tiny points of resistance, and what you get is the sensation of being heavy enough to need a chair, a floor, a planet to stand on. For decades, the Higgs field was only a piece of math on a chalkboard. Then, in July of 2012, scientists at CERN announced they had finally caught direct evidence of it. The Higgs boson, the physical fingerprint the field leaves behind when you disturb it hard enough. In the room where it was announced, Peter Higgs, by then an elderly man who had waited almost 50 years to know if he was right, was seen wiping tears from his eyes as the room rose to applaud him. He later said it felt like being at a football match the moment the home team scores the winning goal. 50 years of uncertainty resolved in a single afternoon, and still there's one more floor beneath all of this. If quarks and electrons are this small, is there a true bottom, a point where smaller stops meaning anything at all? There is. It's called the Planck length, and it's so far beneath the scale of an atom that comparing the two is almost meaningless. If an atom were blown up to the size of the entire observable universe, the Planck length would still only be about as tall as a single tree. Below this point, space and time themselves seem to lose their smoothness and turn into something physicists half-jokingly call quantum foam, a churn where the ordinary rules of before and after, here and there, stop applying cleanly. It is the one wall in the universe that nothing has ever been measured to cross. Nobody has looked at this wall directly. It sits far beyond anything our instruments can reach. It exists in the mathematics, the way a locked door can still be described in perfect detail by someone who has never opened it. But every equation we trust, the same equations that predicted the Higgs field decades before anyone found it, points to the same conclusion. Reality does not zoom in forever. At some floor, the zooming simply stops making sense. The same way asking, "What's north of the North Pole?" stops making sense. Not because we haven't looked hard enough, because the question itself runs out of room. It's worth asking, quietly, where all this strangeness disappears to. Why doesn't a chair behave like a cloud of probability? The honest answer is that it never fully goes away, it just averages out. A single particle can be a blur of maybes, appearing to be in several places at once, until something forces it to settle on one. But group enough particles together, as many as exist in a grain of sand, let alone a chair or a person, and all those uncertainties cancel each other out into something solid, predictable, and still. Nobody has found an exact line where quantum ends and ordinary begins. It's less a wall and more a fade, the way a single drop of rain is unpredictable, but a rainstorm follows patterns you can set your watch to. The strangeness doesn't vanish. It just becomes invisible at the scale we live on. We've now reached the smallest floor there is. There is nowhere further down to go. So from here, there's only one direction left. And it happens to be the same question we opened with, just facing the opposite way. If there's a wall, this absolute on the small end of existence, is there something just as absolute waiting on the other end? Chapter 2: The Solar System and a New Way to Measure. We built our sense of distance on a planet where a kilometer feels like a real walk and a mountain feels like the edge of what's climbable. That instinct is useful here. It is completely useless the moment we leave the ground. Start close. The moon sits about 384,000 kilometers away, roughly 239,000 miles. Light covers that gap in a little over a second, but if you tried to drive there at a steady 100 kilometers an hour, about 60 miles an hour, without ever stopping to sleep, eat, or refuel, you'd still be on the road nearly 5.5 months later. That's the nearest object in the entire sky, the one so familiar we forget it's a destination at all. Now push further, out to the sun, about 150 million kilometers away, or 93 million miles. Light takes around 8 minutes and 20 seconds to cross that distance. That means the sunlight warming your skin right now left the sun's surface before you finished your last thought. If the sun somehow vanished this instant, you would keep feeling its warmth and seeing its light for almost 9 more minutes, with no way of knowing anything had changed. Centuries ago, Galileo pointed a simple telescope at the sky and watched tiny moons circling other worlds, proof that Earth wasn't the fixed center everyone assumed it was. What he was really discovering, without quite realizing it, was depth. The idea that the sky isn't a flat ceiling of lights, but a space with distance built into it, layer after layer, reaching back further than the eye can judge. Before that telescope, the sky had always looked like a painted surface, every star and planet pinned to the same invisible dome. Galileo was the first person to prove the dome wasn't there at all. And once you actually plot the solar system to scale, the thing that jumps out isn't how much is in it. It's how little. Shrink the sun down to the size of a large beach ball placed at the center of a football field, and on that same scale, Earth becomes a grain of sand sitting more than 25 meters away, roughly 27 yards, most of the length of the field. Mars is another grain, further down the field. Jupiter, the largest planet, shrinks to something like a marble sitting well past midfield. Neptune, the last planet before the emptiness truly begins, would be sitting in the parking lot outside the stadium, invisible from where you're standing at the 50-yard line. Nearly everything between those specks is open, silent, and cold. Not empty of activity, since charged particles are streaming through it constantly, but empty of anything solid enough to stand on. This changes what our neighborhood even means. On Earth, a neighborhood is houses close enough to walk between. In the solar system, our nearest neighboring world is millions of kilometers away, and the loneliest stretch, the gap between the last planet and true interstellar space, is measured in distances that make the whole inhabited stretch of our solar system look like a single room in an otherwise empty house. This is where kilometers and miles start to lose their usefulness. Even the Sun, at 150 million kilometers away, already produces numbers too large to hold on to comfortably. Push out to the next star, and you'd be writing distances with more zeros than most people can read in one breath without losing count. So astronomers reached for a different ruler entirely. The light year, the distance light itself travels in a single year, moving at roughly 300,000 kilometers, about 186,000 miles, every second. It took a long time to even prove light had a speed at all. Most people once assumed it simply appeared instantly, the way flipping a switch seems to fill a room with light with no delay you could ever notice. In 1676, an astronomer named Ole Romer was timing the eclipses of one of Jupiter's moons and noticed something odd. The eclipses ran late whenever Earth had drifted farther from Jupiter in its orbit, and early whenever Earth swung closer. It didn't make sense unless one thing were true. The light itself was taking longer to reach him when the distance grew. He worked out that the extra distance was adding a measurable delay, and in the autumn of that year, he did something that took real nerve. He publicly predicted that an upcoming eclipse would arrive about 10 minutes later than expected. When the night came, it did. He was off on the exact number. His estimate for crossing Earth's orbit was roughly a quarter short of what we know today. But he was right about the idea, and it was the first time anyone had caught light in the act of taking its time. Here's what makes the light year strange to think about. It doesn't just measure space. It measures time folded into space. Every photon reaching your eye left its source however many years ago that distance represents. Look at a star 10 light years away, and you're not seeing it as it is now. You're seeing a 10-year-old photograph delivered directly to your retina. The night sky isn't a live broadcast, it's an archive. And speed itself deserves one more comparison before we move on, because it's easy to say fast without meaning anything by it. In late 2024, NASA's Parker Solar Probe became the fastest object humanity has ever built, reaching close to 690,000 kilometers per hour, about 430,000 miles per hour, as it swept past the sun. At that speed, you could cross from New York to Los Angeles in about 20 seconds. That is genuinely staggering by any human measure, and it is still only about 0.06% of the speed of light. Light would cover the same distance roughly 1,500 times faster. Our fastest machine, built with every piece of engineering we have, barely registers against the ruler we just introduced. And that ruler is about to become the only one that makes any sense at all. If 8 minutes to the sun already made you feel the size of things shifting, brace for what comes next, because we're about to leave the entire neighborhood behind. Chapter 3: The Nearest Stars and How Far Our Voice Actually Travels. Step outside the solar system, and the first thing waiting for you is silence measured in numbers that stop making intuitive sense. The nearest star to our sun is called Proxima Centauri, and nearest is doing a lot of quiet lying in that sentence. It sits about 40 trillion kilometers away, roughly 25 trillion miles, or 4.24 light years, a figure refined down to a precision of a few thousandths of a light year by the European Space Agency's Gaia satellite. Even our fastest spacecraft, moving at the kind of speeds that count as remarkable by every human standard, would need tens of thousands of years to make that crossing. Not a lifetime, not 10 lifetimes, an entire span longer than recorded human history, just to reach our closest stellar neighbor. Proxima Centauri isn't traveling alone either. It's the quiet member of a 3-star family called the Alpha Centauri system, where 2 brighter stars orbit each other in a slow, decades-long dance, while Proxima trails much farther out on its own vast orbit, dim enough that you could never spot it without a telescope. It was only identified in 1915 by the Scottish astronomer Robert Innes, which means for most of human history, our closest neighbor in the entire galaxy sat in plain sight and remained completely invisible to us, too faint for the naked eye, hiding in the same patch of sky people had been looking at for thousands of years. We now know it has at least one planet orbiting in the zone where liquid water could exist, a reminder that even across this kind of distance, we may not be entirely alone. Though living there would be no easy thing, Proxima is a restless, flare-prone star capable of blasting any nearby world with radiation strong enough to strip an atmosphere in minutes. Distance, it turns out, keeps us just as safe from that kind of neighbor as it keeps us apart from any friendlier one. Here is a distance most people never think to ask about, and one that says more about our place in the galaxy than almost anything else. How far has the human race actually reached? Not our spacecraft, which are slow and few. Our voice, every radio broadcast, every television signal, every transmission we've ever leaked into space since the technology existed. Researchers at organizations like the SETI Institute describe it as a bubble, expanding outward from Earth at the speed of light since the early 20th century, and by the most commonly cited estimate, it has only reached about 100 light-years out. On the scale of our own galaxy, which stretches roughly 100,000 light-years across, that bubble is smaller than a pinprick on a bedsheet. Sit with that for a second. Every war, every love story, every language ever spoken, every argument, every song, the entire history of our species, condensed into a signal traveling outward at the fastest possible speed, has only managed to reach a tiny fraction of our own galaxy. Past its edge, it is as if humanity has never made a sound. Every civilization that might exist beyond that 100-light-year line has no way of knowing we're here, because our signal simply hasn't arrived yet, and won't for centuries more. We are, in a very literal sense, still mostly unheard of, even in our own neighborhood. Zoom out a little further, and stars stop being lonely points and start clustering into families. One of the most famous is the Pleiades, a group of young, hot, blue stars, still wrapped in the faint blue haze of the gas cloud that birthed them, sitting a little over 400 light-years away. We know about clusters like this partly because of an 18th-century French astronomer named Charles Messier, who wasn't even looking for them. Messier's real obsession was hunting comets, and these fuzzy, stationary smudges of light kept fooling him into thinking he'd found one. Annoyed, he started writing down their positions so he'd stop wasting time on them, and in doing so, accidentally created one of the most useful star catalogs in the history of astronomy. Clusters like the Pleiades work like a laboratory, frozen at a single moment. Every star inside one was born at roughly the same time, out of the same cloud, which means astronomers can watch how stars of different sizes age side by side, almost like photographing an entire graduating class the day they were all born, and then checking back on them a million years later. The biggest, brightest stars burn through their fuel in a few million years and die young, brilliant, and short-lived. The smaller, dimmer ones in that same cluster, born on the exact same day, will still be shining billions of years from now, long after their brighter siblings are gone, proof that size and brightness are not the same thing as staying power, in stars or in almost anything else. And then there are the shapes we've been looking at since before we had a word for astronomy, the constellations, which turn out to be one of the more convincing illusions the night sky offers. Ancient astronomers assumed the stars were all fixed to the same distant sphere, painted onto one flat backdrop behind the planets. We now know that idea is completely wrong, and Orion is the easiest place to see why. Betelgeuse marks one shoulder, a swollen reddish star. Rigel marks a foot, blazing blue-white. From where you're standing, they look like they belong to the same close-knit group, hanging at roughly the same distance. They don't. Rigel sits around 860 light-years away. Betelgeuse is far closer, though still hundreds of light-years off. Even Sirius, the single brightest star in the entire night sky, often looks like it belongs to the same region as Orion, yet it sits dramatically closer than either of them, and only outshines Rigel because it happens to be so much nearer to us. None of these stars are neighbors in any real sense. They only appear to line up because of the one specific angle we happen to be viewing them from one small planet, at one moment in time. Shift your position by even a few dozen light-years, and the entire shape of Orion would collapse into something unrecognizable. The constellations were never a map of what's actually out there. They were always a map of where we happened to be standing when we looked up. We've gone from the sun's backyard to a stretch of space where even our loudest signal fades into nothing within a rounding error of the galaxy's true size. And there's still an entire galaxy left to cross before we've even started on the rest of the universe. Chapter 4: Our Galaxy and the Neighborhood Beyond It. If you could step outside the Milky Way and look back at it, you'd see something close to a flattened spiral, arms of light curling slowly around a bright, crowded center, the whole structure glowing faintly against the dark. The kind of shape that looks calm and orderly from a distance, even though every point of light in it is a sun of its own, most likely dragging its own planets along for the ride. It was the astronomer William Herschel, better known for discovering infrared radiation, who first tried to give this shape real dimensions. Working with nothing but a telescope and enormous patience, he spent years simply counting stars in different directions of the sky, treating the galaxy like a puzzle that could be mapped one region at a time, one star count leading to the next. He guessed the sun sat near the middle of it all. He was wrong about that particular detail, but the method itself, patient, systematic counting, region by region, was the first real attempt to treat our galaxy as something with a measurable structure, rather than just a hazy band of light overhead that people had been staring at for as long as there'd been people to stare. We now know the Milky Way stretches roughly 100,000 light-years across, something like 950 quadrillion kilometers, or about 590 quadrillion miles, a number so large it stops being useful the moment you try to picture the zeros, and becomes useful again the instant you just remember the words 100,000 light-years instead. And within that entire glowing structure, we don't live anywhere near the center. We're tucked into a smaller side branch called the Orion Arm, roughly halfway between the crowded core and the emptier outer edge, suburbs, essentially, on a galactic scale. The true center is so dense with stars and dust that visible light can't even get through it. Only radio waves and infrared, which pass through dust more easily than ordinary light, have let astronomers peer into what's really happening there. And what's happening there is worth pausing on. At the very heart of the Milky Way sits a supermassive black hole, a concentration of mass equal to roughly 4 million suns, crushed into a region not much bigger than our own solar system, known to astronomers as Sagittarius A star. We can't see it directly, since by definition no light escapes it. But for years, astronomers tracked individual stars whipping around that invisible point, at speeds that would tear apart anything less extreme, tightening their orbits around something that gave off no light of its own. In 2022, the Event Horizon Telescope collaboration finally released a direct image of the glowing ring of hot gas surrounding it. Not a picture of the black hole itself, which is invisible by nature, but the closest thing to a photograph of the shadow it casts on everything nearby. For a long time, most astronomers assumed the Milky Way was the entire universe, a single island of stars, surrounded by nothing but darkness on every side. Some of the faint, fuzzy patches Messier had catalogued didn't fit that picture, though. Their distances kept coming out wrong, too far, too inconsistent, as if they existed outside the island entirely, refusing to sit neatly inside the one galaxy model everyone had assumed was correct. In 1755, a German philosopher named Immanuel Kant proposed something audacious, with no real way to prove it. Those weren't clouds of gas at all. They were other galaxies, entire island universes just like our own, sitting impossibly far away, each one its own separate world of stars. Nobody could test the idea at the time, and it was mostly ignored for almost 2 centuries, filed away as an interesting guess with no evidence behind it. Then, in 1929, Edwin Hubble pointed the most powerful telescope of his era at exactly those objects and found the proof. They truly were separate galaxies, at distances nobody had thought possible. Kant had been right, a century and a half before anyone alive could confirm it, which might be the longest wait in scientific history for someone to be proven correct. That discovery gave us our real address. We belong to something called the local group, a gathering of galaxies bound together by gravity, drifting through space as one loose, interconnected family rather than isolated islands. Ongoing surveys now put the confirmed membership at well over 100 galaxies, mostly small, faint dwarf galaxies that are still being discovered as our instruments improve. A steady upward revision from the roughly 50 figure that older documentaries still repeat, and a number that will likely keep climbing. Most of these dwarf galaxies are almost embarrassingly modest by galactic standards, holding only a few million or a few billion stars, where a full-size spiral like ours holds hundreds of billions. Faint enough that entire ones have been discovered hiding in our own cosmic backyard within the last few decades, simply because they were too dim and too small to have been noticed sooner. The dominant member of the group is Andromeda, a spiral even larger than our own, sitting about 2.5 million light-years away, somewhere around 15 quintillion miles, or 24 quintillion kilometers. Light reaching our telescopes from Andromeda left its surface before a single human being had ever walked upright on this planet, traveling silently through the dark for the entire span of human evolution just to reach your eyes. On a clear, dark night, away from city lights, you can actually see it yourself, without any equipment at all, a faint smudge in the sky that looks like nothing more than a slightly blurry star, and is in fact the most distant object the naked human eye can ever hope to see. For decades, popular science treated the eventual collision between Andromeda and the Milky Way as an all but certain event, arriving in roughly 4 to 5 billion years, described so confidently it became something like common knowledge. A more careful study, published in 2025, running 100,000 different simulations and feeding in the most precise motion data available from 2 major space telescopes, found the truth is far less settled than the popular version suggests. Only about a 2% chance of a direct collision within 5 billion years, and closer to a coin flip, 50-50, over 10 billion years. The 2 galaxies are moving toward each other. That part is real. But the exact choreography of a collision this far in the future, factoring in every other galaxy tugging at both of them along the way, is still, honestly, unknown. Even our confident predictions about the deep future turn out to have more uncertainty folded into them than the highlight reel usually lets on. Every one of these discoveries follows the same quiet pattern. We assumed we were the whole picture, and each time, it turned out we were a smaller and smaller part of something larger. The Milky Way once seemed like all there was. Now it's a single house in a modest neighborhood, and the neighborhood itself is about to look very small too. Chapter 5: Superclusters, the Great Nothing, and the Pull We Can't Explain. Galaxies, it turns out, don't scatter through space at random. They gather into clusters, and then into something even larger, the way towns gather into counties, and counties gather into states. And the first hint that something invisible was holding those gatherings together came from an astronomer most of his colleagues found difficult to work with. In the 1930s, Fritz Zwicky, an astronomer known as much for his sharp tongue as his sharp mind, was studying a crowd of galaxies known as the Coma Cluster, sitting an almost unbelievable distance away, somewhere in the range of 10 million trillion kilometers, or roughly 6 million trillion miles. He measured how fast individual galaxies inside that cluster were moving, and the numbers didn't add up. At those speeds, based on the visible mass he could see, the whole cluster should have flown apart billions of years ago, scattering in every direction like a crowd with no fence around it. It hadn't. Something was holding it together that no telescope could detect. Extra mass, invisible, exerting gravity without giving off a single photon of light. Zwicky called it dark matter, and for decades, the idea sat on the fringes of astronomy, treated as an odd fix for numbers that didn't quite work, more curiosity than confirmed physics. Decades later, the astronomer Vera Rubin confirmed he'd been onto something real. Standard physics predicted that stars near the outer edge of a spiral galaxy should orbit slower than stars close to the center, the same way outer planets orbit the sun more slowly than inner ones. Rubin found the opposite. Stars at the edges of galaxies were moving just as fast as stars near the core, as if some unseen mass were spread evenly throughout, not just clustered at the center. It was the kind of result that should have been a mistake, the sort of thing you double-check 3 times before believing. She checked and checked again, and the pattern held, galaxy after galaxy. Her measurements, later confirmed across dozens of other spirals, showed that the visible stars, gas, and dust we can actually see account for only a fraction of a galaxy's total mass, something like 1 part in 10. The rest is there, exerting a real, measurable gravitational pull, and remains completely invisible to every instrument we've ever built. We have never once seen dark matter directly. We only ever see its fingerprints in the way everything else moves around it. Our own region of this dark, gravity-bound structure is dominated by the Virgo cluster, home to roughly 2,000 galaxies, pulling on our own local group with enough force that we are, quite literally, falling toward it, drifting a little further into its gravitational grip with every year that passes. Zoom out again, and the Virgo cluster is itself just one piece of the larger Virgo supercluster, a structure spanning more than 100 million light-years, somewhere around 590 quadrillion miles. At this scale, entire galaxies stop looking like individual objects and start looking like single grains of light scattered across the nodes of an enormous, invisible net. The way a single city light looks like nothing more than a dot from an airplane window at cruising altitude. This is also the point where the word cluster stops meaning what it means on Earth. A cluster of houses is a few dozen buildings within walking distance of each other. A cluster of galaxies is thousands of entire star systems, each one containing hundreds of billions of suns, held together across a gap so vast that light itself needs tens of millions of years just to cross from one side to the other. But even a net this large has holes in it, and one of them is enormous. In 1981, the astronomer Robert Kirshner and his team found a region of space nicknamed the Bode's Void, colloquially, the Great Nothing. It measures somewhere around 250 to 330 million light-years across, nearly 2 quintillion miles, and inside it, astronomers expected to find roughly 2,000 galaxies based on the density of everywhere else nearby. They found around 60. Scattered that thin, those 60 galaxies would look less like a neighborhood and more like a handful of distant porch lights left on across an entire dark continent. If our own Milky Way had happened to form inside that void, instead of where it actually sits, we might not have known any other galaxies existed until the middle of the 20th century. The nearest lights would have simply been too far away for older telescopes to catch. We would have looked out at total blackness in every direction and reasonably concluded with total confidence that we were the only thing in existence. It's a strange kind of comfort to know we were spared that particular kind of loneliness only by an accident of where we happened to form. Zoom out once more, past our own supercluster, and something stranger appears. We, along with the Virgo supercluster and everything in it, are part of an even larger structure named Laniakea, immeasurable heaven in Hawaiian. Identified only in 2014, once astronomers finally had the tools to track the actual motion of galaxies rather than just their positions. Before that, we had simply been guessing at our address based on which clusters looked closest on a map. Laniakea was the first time anyone actually followed the traffic, watching which way every galaxy nearby was truly moving, rather than just where it happened to be sitting. Think of it less like a map and more like a watershed, the way rain falling on one side of a mountain ends up in a different river than rain falling on the other side. Every galaxy in this region is being slowly drawn along the same invisible current, toward the same destination. Laniakea spans roughly 520 million light-years, containing something on the order of 100,000 galaxies, all moving together as one enormous, gravitationally bound system, and within it, something is pulling everything, including us, in one specific direction, a concentration of mass astronomers call the Great Attractor. On this new map, the Virgo supercluster, the very structure that once seemed to define the outer edge of our understanding, turns out to be little more than a side branch of a much larger river system, one small tributary feeding into something vastly bigger. We cannot see it directly. It sits hidden behind the dense core of our own galaxy, in a region so thick with stars and dust that it's known, appropriately, as the zone of avoidance. Our own galaxy is, quite literally, standing in the way of us understanding what's pulling us toward it. A 2024 radio survey called Wallaby, using signals that can pass through dust that blocks ordinary light, managed to refine our sense of exactly where it sits and how strong its pull really is. Somewhere in the neighborhood of 10 quadrillion times the mass of our Sun, likely centered around a dense knot of galaxies called the Norma cluster, though even that remains partly obscured behind our own galactic skyline. Here is the strange part. We are being pulled toward the Great Attractor, right now, at roughly 1.4 million miles an hour, and the most careful calculations we have suggest we will never arrive. Chapter 6: The Force That Never Loses, and the Largest Thing We've Ever Found. To understand why a pull this strong might never actually bring us home, we need to talk about a discovery that stunned the people who made it, back in the final years of the 20th century. Until the late 1990s, nearly every astronomer assumed the expansion of the universe had to be slowing down. It made intuitive sense. Everything in the universe has mass. Mass creates gravity, and gravity pulls things together. So the expansion that began with the Big Bang should have been acting like a ball thrown into the air, decelerating the whole way, eventually curving back down, maybe even reversing into a slow collapse someday. In 1998, a team led by the astronomer Adam Rees set out to measure exactly how much that expansion was slowing, using a very specific, very reliable kind of exploding star called a Type 1Ia supernova, bright and predictable enough to work like mile markers scattered across the universe, each one a known brightness you could use to calculate distance with real confidence. What they found instead was the opposite of what everyone expected, and at first, some of them assumed they'd simply made an error somewhere in the math. The most distant galaxies weren't just moving away from us, they were accelerating away, picking up speed the farther out you looked, like a ball thrown into the air that suddenly rockets upward instead of falling back down. Every model anyone had built up to that point had gotten the ending of this story backwards. Nobody had a name for whatever was causing it, so they gave it one anyway: dark energy. The discovery was considered significant enough that Rees and his colleagues were awarded the Nobel Prize in Physics in 2011, a remarkably fast turnaround, as these things go, for a finding that upended one of the most basic assumptions in cosmology. We still don't know precisely what dark energy is. We do know it appears to make up roughly 2/3 of everything that exists, and that it behaves like a kind of pressure built into space itself, pushing outward, everywhere, all the time. Picture the universe less like an explosion flying outward through empty space, and more like a loaf of bread rising in an oven. The raisins inside don't move through the dough on their own, they simply drift apart because the dough between them keeps expanding. That drift is dark energy, and it means the great attractor, however strong its pull feels, is losing a race against something even stronger, the space between us, and it is stretching outward faster than gravity can close the gap. Every galaxy we'll ever chase is standing on a floor that keeps sliding away beneath it. It's a strange, quietly sad footnote to all of this. Because of that expansion, there are galaxies visible in our telescopes right now whose light will eventually stop reaching us altogether. The space between us and them is stretching fast enough that, one day, their glow will simply run out of room to arrive. So does anything sit beyond Laniakea and the pull we can't escape? It does. And this is where the scale of things gets almost impossible to hold in your head. In February of 2025, an astronomer named Hans Bohringer, working at the Max Planck Institute for Extraterrestrial Physics, published something extraordinary: a newly mapped megastructure of galaxies stretching roughly 1.3 billion light-years across, given the name Quipu, after the knotted cords ancient Andean cultures once used to keep records of numbers and events long before written language reached them. It is the largest structure of galaxies ever directly mapped and confirmed, a chain of clusters and filaments so vast that, by most calculations, it shouldn't exist at all. Cosmology has a working assumption called the cosmological principle. Zoom out far enough, and the universe should look roughly the same everywhere, an evenly mixed soup with no single lump larger than about 1.2 billion light-years. Quipu is close to that limit and arguably exceeds it, forcing physicists to ask whether the early universe seeded far more structure than our models currently allow for, or whether gravity, at these scales, still has surprises left to reveal. Either answer means our best equations are still missing something, somewhere, about how the largest things in existence came to be. There is one structure people often describe as even larger still, something called the Great Wall of Hercules Corona Borealis. It was found in 2013 by the Hungarian astronomer István Horváth and his team, who weren't looking for a galactic structure at all. They were mapping gamma-ray bursts, the single most violent flashes of light in the universe, usually released by the death of a massive star or the collision of two extreme objects like neutron stars. Somewhere between the constellations Hercules and Corona Borealis, they noticed those flashes clustering together far more densely than random chance should allow, as if something enormous and otherwise invisible were concentrating them in that one direction. Following that clustering out, the estimated structure stretches roughly 10 billion light-years across. It's worth being honest about its status, though, because it was found indirectly, through a statistical clustering of bursts rather than a direct galaxy survey. A real number of scientists consider it a possible statistical artifact rather than a confirmed physical structure, the astronomical equivalent of seeing a shape in a cloud that might not actually be there once you look from a different angle. Quipu, by contrast, has been mapped and confirmed directly. So if we're being precise, and precision has mattered every step of this journey, Quipu is the largest structure of galaxies confirmed to exist. The Great Wall may be larger still, or it may be a trick of the numbers. Either way, it stands as the outer edge of what we've been able to measure, honestly, so far. And that, right there, is worth pausing on. We have walked all the way from a wall smaller than anything measurable to a structure that may or may not even be real, stretching across a meaningful fraction of everything we can see. Two walls, one at the very bottom of existence, one, possibly, at the very top, and in between them, every atom, every star, every galaxy, every single thing that has ever happened, including whatever thought you're having right now. The honest answer, after all of this, is that neither wall is fully settled. The smallest one exists only in equations nobody has ever directly tested. The largest one might not exist at all in the way we've described it. That uncertainty isn't a failure of the journey. It's the most accurate place a journey like this can actually end. We know an enormous amount about the space between those two walls, about the edges themselves. We are still, honestly, guessing our way forward, one careful measurement at a time. It's tempting, standing at the edge of a scale like this, to feel like a rounding error, a speck too small to matter, on a stage too large to care. But that framing misses something. We are not visitors passing through this structure from the outside, peering in through a window. We are made of it. The calcium in your bones and the oxygen filling your lungs right now were forged in the same kind of stellar furnaces that scattered the raw material for galaxies like the ones inside Quipu, billions of years before there was anyone alive to wonder about any of it. There is no separate physics for the very large and the very small, and no separate substance for the universe and for you. When you trace the path from the Planck length to the largest confirmed structure in existence, you are tracing your own ingredients the entire way. Every step of that walk was, in some very real sense, a walk through your own history. Somewhere in the space between a wall too small to cross and a structure too large to fully confirm, matter arranged itself into something that could ask questions about both. That's not a small thing. Most of the universe, as far as we can tell, is simply doing what physics tells it to do, moving without noticing, existing without wondering. And then, on one unremarkable planet, orbiting one unremarkable star, tucked into the suburbs of one ordinary galaxy, some of that matter woke up enough to look outward and start counting. Every one of the numbers in this journey came from that same small, stubborn habit. Someone, somewhere, refused to accept "we can't know that" as a final answer. A man counting eclipses of a distant moon. A woman patiently rechecking a measurement that shouldn't have been true. A team pointing an instrument at a patch of empty-looking sky, simply to see what was actually there. None of them could see the whole picture we've walked through here. Each of them only added one more piece, one small correction to how big we understood things to be, and somehow, added together across centuries, those small corrections are exactly how a species standing on one grain of sand ever managed to measure a beach this size at all. The scale of the universe was never really a measurement of how small you are. It's closer to the opposite, proof of how far raw matter had to travel through supernovae and collapsing clouds and billions of years of quiet chemistry before it could arrange itself into something capable of understanding any of this at all. You are not an accident standing outside the universe, looking in through a window. You are the part of it that finally opened its eyes.